People were probably astounded by what they were seeing because clearly the ocean floor had enormous changes in relief, was very mountainous in some places, had great deeps in other places.
There's a shrimp that grows to the length of your forearm, a jellyfish with no tentacles, just arms, 4 of them, each stretching meters behind it in the dark. A single cell, 1 cell, that grows large enough to hold in both hands. And a squid drifting somewhere in the black water above the ocean floor, with eyes the size of footballs.
Jellyfish, phantom light, 200 meters down in pitch black. Our next story telling you more about.
None of these creatures live anywhere near the surface. None of them live in warm water, or rich water, or water with any real food in it. They live in the coldest, darkest, most starved environment on the planet. A place where the pressure builds strong enough to flatten steel. A place where the floor drops so far that if you sank Mount Everest into it, the summit would still drown under a kilometer of water. The Mariana Trench, the deepest place on Earth.
This is the Mariana Trench, the deepest known part of the Earth's oceans.
And by every rule of biology, this place should produce the smallest creatures alive, not the largest. So why doesn't it? Why does the most hostile environment on the planet keep growing giants? Is it the cold, the pressure, the absolute dark that hasn't been broken by a single ray of sunlight in millions of years? Scientists have studied this for over a century. They still don't fully agree. Because the answer, as it turns out, isn't one thing. It's everything. All at once, working together in a place that was never supposed to support life this large. And in March of 2025, researchers filmed something alive that we had only ever seen dead or in pieces. A creature so extreme it had avoided every camera ever pointed into the deep. We'll get to that. But first, let's start with something you've definitely seen before. You know the pill bug. That small gray creature that rolls into a perfect ball when you touch it. Harmless. The kind of thing children collect in gardens and carry around in their palms. It fits comfortably on your fingernail. Now take that animal. Keep everything. The segmented armor, the jointed legs, the curved body. Keep all of it. And make it the size of a football.
Look at how cool these are. I mean, I cannot believe we are standing right in front of this many deep sea giant isopod. We've got 1, 2, 3, 4, 5, 6, 7, 8 giant isopods.
That is the giant isopod. It scuttles across the abyssal plains of the deep Atlantic and Pacific, reaching 50 centimeters long and weighing over a kilogram. It moves without urgency, without fear, without any visible awareness that something has gone profoundly wrong with its sense of scale. When food finally arrives, a dead fish, a carcass drifted down from thousands of meters above, it feeds until it physically cannot move. A scavenger built like armor, patient as stone. The first question is why it got this big at all. And the answer starts with something as simple as temperature. Cold water holds more dissolved oxygen than warm water. Significantly more. And oxygen is everything. It fuels every cell, every muscle, every heartbeat. In the warm tropical shallows, oxygen is limited. Growing too large becomes a liability. Your cells simply cannot pull in enough oxygen fast enough to support a massive body. The warm sea quietly sets a ceiling on size. But the deep is cold. Permanently, brutally cold. Just above freezing, year-round, without variation. And that cold water is saturated with dissolved oxygen. More than enough to support larger tissues, larger organs, larger everything. The ceiling lifts. At the same time, that cold slows down metabolism. Every chemical reaction that powers a living body, burning fuel, firing nerves, repairing tissue, all of it happens more slowly in the cold. For a land animal, a slow metabolism is a death sentence. You become sluggish, easy prey, outcompeted. But in the abyss, slowness is power. When your body burns energy at a fraction of the normal rate, you can survive stretches of starvation that would kill anything from the surface world. The giant isopod can go over a year without a single meal. It doesn't need to hunt constantly. It doesn't need to stay warm. It can simply wait in the dark, burning almost nothing, outlasting the famine. And in a place where meals arrive weeks apart, waiting is the only strategy that works. So cold water does two things simultaneously. It gives you more oxygen to build a larger body, and it slows you down enough that the larger body doesn't cost too much to run. But here's the thing. Cold and oxygen explain the ceiling. They don't explain the creature. Something else is driving animals in the deep toward size, and it's darker than temperature. Take the Japanese spider crab. Its body is compact, rounded, modest, but its legs stretch nearly 4 meters from claw to claw, making it the largest arthropod alive on Earth.
Spider crabs.
It stalks the ocean floor in slow, deliberate arcs, picking through sediment for scraps. It can live for 100 years, a century of slow growth, each year adding fractionally to those extraordinary limbs, until it becomes something that looks less like a crab and more like a piece of walking architecture. It is patient in the way only deep-sea creatures can be. It doesn't chase. It doesn't rush. It exists in geological time, indifferent to urgency, built for endurance rather than speed. That patience is not an accident. It is the direct result of the second force driving gigantism in the deep. The deep sea is not just cold. It is hungry. There are no plants, no photosynthesis, no fresh energy manufactured from sunlight. The entire ecosystem runs on what falls from above, the slow, constant drift of particles scientists call marine snow. Dead plankton, shed skin, fecal pellets, fragments of creatures that lived and died in the sunlit waters thousands of meters overhead. By the time this drift reaches the abyss, most of its nutrients have already been stripped away by creatures higher up. What arrives at the trench floor is barely a ration. In a world this starved, a small body with a fast metabolism is a disaster. You burn through your reserves quickly. Food doesn't come. You starve. A larger body with a slower metabolism rewrites that equation entirely. You need less energy per unit of mass. You spend less. You endure more. The Japanese spider crab can absorb months of hunger without shutting down because its sheer size gives it fat reserves that smaller crustaceans simply don't have. It is playing a different game entirely, one measured not in days, but in decades. Larger bodies are better at waiting. Size in the abyss is a battery. The bigger you are, the longer you last between charges. This is what deep-sea gigantism actually is. At its core, it is not a side effect of the environment. It is the environment's preferred solution to the problem of survival. Grow large, slow down, endure. But here's what no one tells you. That strategy has a hard limit. Follow the trench all the way to the bottom, past the abyssal plains, past the midnight zone, down into the Haddle zone where the walls close in and the pressure crosses 1,000 times atmospheric, and the giants begin to disappear. Not because the physics change, but because the food runs out entirely. The marine snow that drifts down from above has been consumed, stripped, and reconsumed at every layer above the trench floor. What reaches the absolute bottom is almost nothing. And a giant body, for all its efficiency, still needs more than almost nothing. At this depth, the only creature that rules is the Mariana snailfish, the deepest living fish ever recorded.
A new record has been set for the deepest fish ever recorded. And according to scientists, this species isn't even meant to be a deep-sea fish. Imagine being 5 miles below the surface of the ocean and seeing this little guy. a snailfish.
And it is not large. It is small, pale, and gelatinous. Its skull is partially open so its brain doesn't get crushed inside its own head. Its body is composed almost entirely of water-based tissue that cannot be compressed. Because at this depth, you cannot fight pressure. You can only become it. The snailfish understood something the giants above it never needed to learn. At a certain depth, size stops being a battery and starts being a liability. More body means more fuel required. More fuel required means more starvation. The trench floor doesn't reward the largest. It rewards the leanest. The Mariana Trench, then, is not just a factory for giants. It is a scale. It measures exactly how large life can afford to be at each depth, and it enforces that limit with absolute precision. Higher up, where food is more available and pressure slightly less extreme, evolution pushes toward size. Lower down, where the arithmetic becomes brutal, it pulls back. The giants don't live at the very bottom. They live in the sweet spot, the precise depth where the balance tips in their favor. And in those waters, in that exact zone, one more force shapes everything. In shallow tropical water, everything is a potential meal. Reef predators, pelagic hunters, great white sharks, dolphins, orcas. Competition arrives from every direction, every angle, every depth. In that world, being small is survival. You hide in crevices, you dart away, you disappear into a school of thousands. Size draws attention. Attention gets you killed. The shallow sea enforces smallness the way attacks enforces compliance, constantly, invisibly, without mercy. But in the deep, the great predators of the surface world don't exist. The hunters of the midnight zone are specialists built for ambush, not pursuit. The anglerfish dangles its glowing lure and waits. The dragonfish illuminates prey with a red searchlight no other creature can see. The gulper eel opens a mouth that stretches to impossible proportions and hopes something wanders in. These are patient, precision killers. They hunt small. They don't chase giants. When predators stop enforcing smallness, size becomes possible. When size becomes possible, evolution experiments. When evolution experiments over millions of years of perfect stability, undisturbed by the chaos of seasons and tides and temperature swings, it eventually arrives at something extraordinary. Consider the giant phantom jellyfish, Stygiomedusa gigante. It has a bell over a meter wide. It carries no traditional tentacles, only 4 enormous ribbon-like arms that trail behind it for meters in the current. It moves without sound, without urgency, without any visible effort. A ghost the size of a dining table, drifting through water so cold and dark that even the concept of shadow doesn't apply. In over 100 years of deep-sea exploration, it has been spotted fewer than 100 times. It is that large because nothing in its environment has ever needed it to be small. No predator selected against its size. No food shortage demanded it shrink. It simply drifted, generation after generation, in an environment that removed every reason not to grow, until it became something that has no equivalent anywhere near the surface. This is called the predation release hypothesis. Remove the pressure to stay small and fast, and life drifts toward size. Not because size is better in any absolute sense, but because in the absence of the forces that punish it, size is simply what happens. Now. March 2025. A research vessel positioned near the South Sandwich Islands drops a remotely operated vehicle into the water. It descends, nearly 600 meters. The camera feeds back to the surface in real time. And there, drifting in the dark, is something that has existed in sperm whale stomachs and washed-up carcasses and fishermen's myths for centuries, but has never, not once in all of recorded human history, been confirmed alive on camera. The colossal squid. Meso-Nicoteuthis hamiltoni. The largest invertebrate alive on Earth. This particular individual is a juvenile, barely 30 centimeters long, a child by colossal squid standards. But even at that size, the camera catches the detail that defines the species, those eyes. Disproportionate, enormous, already far too large for the body they sit in. Adult colossal squid have eyes the size of footballs, the largest eyes of any creature ever documented. Not because evolution was being dramatic, but because in permanent darkness, larger eyes catch more of the faint bioluminescent flickers that constitute the only light available. Every millimeter of additional eye diameter is the difference between seeing a sperm whale approaching and not seeing it, between striking first and being swallowed. The colossal squid weighs over 500 kilograms. Its tentacles are lined not with suckers, but with rotating hooks, serrated, swiveling, designed to grip and tear. It battles sperm whales in the deep, leaving scars across their skin that scientists track across entire ocean basins. It is by every measure a product of everything the deep does to life when it works on it long enough. The cold gave it the oxygen to grow this large. The scarcity trained it to conserve energy across months without food. The absence of predators allowed it to grow without evolutionary pressure towards smallness. The isolation of the deep Pacific refined it over millions of years without the disruption of the surface world. Every force we've talked about converges in this one animal. And we saw it alive for the first time in human history 6 weeks before the writing of this script. A juvenile, a glimpse. We have never filmed a full-grown adult in its natural habitat. We don't know exactly how large they get. We don't know how long they live. We know they fight sperm whales because of the scars. We know they exist in the deep Southern Ocean because of the beaks found in whale stomachs. Everything else is inference, estimation, and the occasional battered carcass on a New Zealand beach. The largest invertebrate alive on Earth remains, in almost every meaningful sense, unknown. For centuries, sailors told stories of monsters. The Kraken, a creature so vast it could be mistaken for an island, rising from Norwegian waters to drag entire ships beneath the surface.
But is this just a legend? Or could some kind of monster really be lurking beneath the surface?
Sea serpents coiling around hulls in the dark. Beasts too large to comprehend, hauled up in nets already half dead and decomposing. Their enormous eyes staring at the surface world from the deck of a ship as if they couldn't quite believe it existed. These weren't fantasies invented by frightened men. They were observations made by people who had no framework for what they were seeing. A giant squid washing ashore in the 18th century, its body already decomposing, its beak exposed, its basketball-sized eyes still intact. That would look like a monster to anyone. Because it is one. Just not the kind they imagined. The myths were wrong about the malice, right about the scale. What's stranger than any legend is the actual answer to why these creatures exist. They are not monsters. They are the outcome of a simple, brutal logic that the deep sea has been running for 400 million years. Remove warmth, remove light, remove food, remove predators, add cold and pressure and infinite patience. Then wait. What you get is not horror, it's engineering. Bodies designed with a precision that makes our best technology look improvised. Eyes tuned to detect a single photon. Hooks engineered to grip something the size of a bus. Metabolism so efficient they make hibernating bears look extravagant. We have explored less than 20% of the ocean floor. The Mariana Trench, all 2,500 kilometers of it, has been meaningfully surveyed in a handful of locations. Every mission returns with something that forces biologists to revise what they thought was possible. Every camera sent down comes back with footage of animals that don't match anything in the existing literature. In 2025, we finally saw a colossal squid alive. A juvenile. The full-grown adult, the one leaving scars on sperm whales, the one with eyes the size of footballs. The one that represents the full expression of everything the deep can do to a living thing, remains entirely unfilmed. What else is down there, fully grown, at full depth, in the 2,500 kilometers of trench we haven't looked at yet? What else has the cold and the dark and the pressure and the patience been building? The trench doesn't give up its inventory easily. Every answer it offers arrives alongside 3 new questions. And somewhere in that dark water, in the exact depth where the balance tips just right, not too deep to starve, not too shallow to grow, something is drifting that no human eye has ever seen. Something that has had 400 million years to become exactly what it is. And we haven't sent a light down far enough to find it yet.